For the first talk of the day, we have Joerg Frauendiener, who's going to tell us about a unified treatment of energy momentum at infinity.
Thanks, and it's a pleasure to speak here, and I'm grateful to the organizers to invite me. So, yeah, let's get started. So I will be talking about a project that goes back really until 1980-something, which is based on work that Gary Horowitz and Paul Todd have been doing then. And it's related to the various representations or treatments of energy momentum in GR. We know that this is well defined only in the infinite regions, asymptotically. And the problem is that there are two different asymptotic regions. There is null infinity and there is space-like infinity, and we have different concepts for those. And Gary and Paul tried to merge this together, but they went a long way, but there are still some gaps, and I am trying to, well, not completely, because this is still work in progress, but I try to convince you that those gaps can be closed. So what's this about? So here is the idea of energy momentum in GR. We have the energy momentum based at space-like infinity, which is defined on an asymptotically Euclidean hypersurface with a metric h. And this is originally due to Arnovides and Misner. That's why it's usually called the ADM energy momentum. And it describes the total energy momentum that is contained in the spacetime. So we have an asymptotically flat spacetime, I should say. So all of this applies to asymptotically flat spacetimes with vanishing cosmological constant. And so the ADM energy momentum is really a 4-vector on the space of asymptotic translations. And so when you give an asymptotic translation, you integrate a certain expression against this at infinity, at the sphere at infinity, and you get a component of this energy momentum. So when you take a time translation, you get an energy. When you take a space translation, then you get a component of the momentum. And it turns out that the energy component is positive. No, this is at space-like infinity. So you look at transformations that have certain properties, and I'm not going to go into this because this develops into a whole mess. So, so the main contribution in the ADM regime was the proof that the ADM mass is positive, which was given by Witten in 1980, based on spinor methods. So he had this insight that you can essentially take the square root of a vector by writing it in terms of a spinor, and this was a very useful idea. So the idea is the following: that you have your asymptotically Euclidean hypersurface, and on this hypersurface you look at a solution of a certain PDE or system of PDEs, which is now called the Witten equation. That's this equation here, so that's a two-component spinor. Where you take this equation, where this D operator here is the projection of the space-like connection, of the space-time connection onto the surface, and it operates on vectors and spinors, but it is not exactly the same as the induced Levi-Civita connection of this metric here, but it has vertical components. So if you would write it in terms of the induced Levi-Civita connection, you would pick up a term that comes from the extrinsic curvature of your hypersurface. So that's the Witten equation, and then you can define a null vector by taking the product of the spinor and its complex conjugate. That gives you a null vector, and then you do a calculation where you look at the derivative of this null vector here, and integrate this over a sphere at infinity using the Stokes theorem. You can rewrite this. You can rewrite this by taking another exterior derivative of this expression, and then you can use the the Witten equation in order to produce two terms, one of which is related to the energy momentum content of the space-time. So that's the energy, that's the matter energy momentum tensor. It's not the energy momentum tensor that would come from a spin field. We regard the spin field here as a test field. And you have this term here, which is manifestly, including the minus sign, is manifestly positive. And so if you have a dominant energy condition, like this, what this DEC stands for, then this term is positive, this is positive, and so the entire thing is positive. And by rewriting this surface integral, you find that asymptotically this evaluates to a component of the ADM energy momentum. Okay, so this gives you the idea that every null component of the ADM energy momentum is positive, and so that's why the time components are also positive. So that's the Witten argument, and its importance is the fact that it uses the spinors. Then we have the other asymptotic regime, which is the scry, which is null infinity, and on every cut of scry we can define the Bondi mass or the Bondi-Sachs mass, and this describes the energy momentum at a certain constant, at a certain instant of time, which is given by the cut. So this is retarded time, as you would do usually on scry. So it's what people call U. U equals constant. And again, this is interpreted in the same way that you look at asymptotic translations, now as defined on scry, and the Bondi-Sachs energy is obtained by integrating a certain expression, the mass aspect, against an asymptotic translation. Again, when you take a time translation, you pick up the Bondi-Sachs energy. When you take a space translation, you pick up a component of the Bondi-Sachs energy, Bondi-Sachs momentum. We have the fact that the energy is positive, and we also have the mass loss. So this is that's the Bondi-Sachs mass loss, which was proven in 1962 by Bondi-Sachs, and Trotman had an early version of this. And so when you look at the Bondi-Sachs mass at an instant of time and compare it to a later instant, you find that the mass has gone down, and the difference is due to the energy that was taken away from the system by gravitational waves. After the Witten proof for the ADM positivity, or ADM mass positivity, various people try to apply this also in the context of the null infinity, and I'll just pick the Ludwigsen-Vickers argument, where they take a spinor and propagate the spinor according to some propagation law along asymptotically null space-like hypersurfaces, and they can also show that under certain conditions the all null components of the Bondi energy momentum are positive. So that's the story of the energy momentum in the two regimes. Pictorially, we have this picture here. So when you have an asymptotically flat spacetime, you have your scries, scry minus and scry plus. This here is the asymptotically Euclidean hypersurface. And you expect that, and in Minkowski space, that would be the case, that the scry plus and the scry minus, when you extend them to the future or the past, that they meet in a point where also this sigma here ends up. But this is only true in Minkowski space, and for a general asymptotically flat space-time, you do not know exactly what's happening here in this area where these asymptotic regimes are coming together. I've indicated here that the Bondi mass that you can also define on Scri minus increases towards the future, whereas on Scri plus it decreases towards the future, so it increases towards the past. Okay, so and we are concerned here about this region here. So can we find a common description of energy momentum that is valid everywhere? So the paper by Horowitz and Todd in 1982 tried to do something like this, and what they tried was, or what they came up with was to instead of using the Witten equation, which is an equation that lives on an asymptotic, well, on a space-like hypersurface, on a three-dimensional thing, they wanted to do this in a four-dimensional thing, and the easiest and the most straightforward generalization of the Witten equation into the four-dimensional context is the Weil equation. And so you take a solution of the Weil equation. When you write this down in coordinates and you look at this from the point of view of PDEs, you find that this is a system of well, two equations, and it gives you a symmetric hyperbolic system. So it has a well-defined Cauchy problem, and so it's a good equation. And then Gary and Paul go on to again define the null vector that is related to the spinor, and from this null vector they define a one form, a covector, as the if you want the current that is defined by the potential that is given by this by the null vector here. So you take the curl of this, that would give you an electromagnetic field, if you think about it in this way, and then you take the divergence, and that with the second Maxwell equation gives you a current, and so that P here is the current of the electromagnetic potential defined by this null vector here. And then you do the same thing as I did before. You integrate this equation over a three-dimensional hypersurface. You find that you can write this using the Stokes theorem as a surface integral over the sphere at infinity, if you extend things to infinity. And then when you use the equation here, you find that the P here gives you this expression, or is given in terms of this expression. So this is the contraction of the derivative of the spinor, where you have already used the fact that the contraction of this thing here is equal to 0. Okay, so it looks like the two terms in the Witten argument. So when you look at these things on a asymptotically Euclidean hypersurface, so you take a sigma, and you notice that what I said earlier, the Weil equation is has a well-posed Cauchy problem. Then you need to give initial conditions. You can give initial conditions on this hypersurface and then start the evolution to get the spinor field everywhere in space-time. And the initial conditions can be given freely, so there are no constraints for the Weil equation. So this is a completely constraint-free symmetric hyperbolic system. And so your initial data can be given arbitrarily. In particular, you can demand that your initial conditions satisfy the Witten equation. And then what happens to the derivative of the spin field here, when you decompose this into time and space components, then you get this D here without an index is just the covariant derivative in the direction of the normal T to the surface sigma, and this here is the what's called the Witten derivative or the Witten operator. That's the thing that I showed earlier. And this here is that's the space-time connection, and you decompose this into a time part and a spatial part. That's all. So when the spinor field here, when this alpha satisfies the Witten equation, then we have this relationship here. So we have the contraction of the derivative of alpha is equal to 0, and that means that this term here becomes the Witten operator acting on alpha, which is 0 when alpha satisfies the Witten equation on sigma. And so then we have that the time derivative must be equal to 0 because the TAA prime is regular. So we can invert this. So that means that the time derivative of the spin field is equal to 0, and then we plug that into this equation here, and we find that the derivative of the spin field is just given by the spatial components. And then we get that the P, the density reduces to this thing, and that is exactly what we found in the Witten equation. So that's exactly the two terms that we saw in the proof of positivity using the Witten argument. And so this consideration on an asymptotically Euclidean hypersurface reproduces the Witten argument, but with a spin field that satisfies the Weil equation everywhere. All right, on an asymptotically null hypersurface, which I call here sigma prime, Horowitz and Todd prove this statement here that when you take, so you have an asymptotically flat spacetime, and you have a solution of the Weil equation, and then you suppose that that the spinor field is asymptotically constant in the sense of Bremsen, and I'll talk about this in a second, what it means. So this means that as you go towards null infinity, your spinor field is finite, and so it has finite values on scry, and those values satisfy a certain equation which was invented or found by Brian Bremsen. So if you have these properties, a solution with this property here, then the null vector that you get in the limit is an asymptotic translation, and when you evaluate the integral of the density over this asymptotically null hypersurface, you pick up a null component of the Bondi energy momentum corresponding to this asymptotic translation. So there is a relationship also from the solution of the Weil equation to the Bondi energy momentum. So this vehicle, the Weil equation, actually does give you a connection between the two regimes. And and so the interpretation here is that this P, this covector, acts like an energy momentum density, which includes contributions from the local matter energy momentum and some component of the gravitational energy momentum. I mean, we know that we cannot pin down the energy momentum of the gravitational field at a point, and this is reflected in the fact that this P here is highly non-unique. As you can see, the P depends on the alpha, and the alpha depends on what hypersurface sigma you choose, what initial conditions you choose, and so it is a completely or very non-unique representation or non-unique expression for gravitational energy momentum density. And also what is not known is that this P should be, if it's a bona fide energy momentum density, then it should be future pointing and time-like everywhere. So that's not known. Okay, So I've formulated all this in the physical space-time. We can now go to the conformally related conformal space-time. So now I'm writing the physical quantities with a tilde and the unphysical ones without a tilde, just to not have to write that much. So we have the relationship that the unphysical metric G is conformal to the physical one with the conformal factor omega. And we have to decide about how we deal with the spinor. And so in general, we can do this. We can scale this with some power of the conformal factor. And then we get this relationship here between the derivatives of the spinor. So the derivative, the unphysical derivative of the unphysical spinor is given in this way in terms of the physical derivative of the physical spinor. And this epsilon here, or this gamma kind of thing, is just the gradient of the log of omega. That's the usual convention from Penrose and Rindler. So when you look at this, you find that there are two special values for S. When S is equal to 0, you find that the symmetrized derivative is transforms nicely, so it's homogeneous. If I would raise the E prime here, then it would even be the same. And when S is equal to -2, then the Weil equation is conformally invariant. So now here we want to look at the case where the spinor field, the physical spinor field, actually has finite values when you go to scry. And that means that we have to take S equals 0 because both the physical spinor must be finite. If we took S equals -2, then this alpha here would blow up. And so we choose S is equal to 0, and then we have to look at this equation, which corresponds to, or this equation is the same as the physical Weil equation. And then we have that the symmetrized derivative is equal to 0 on scry. Sorry, the symmetrized derivative is invariant, and the Bramson boundary condition is exactly that the symmetrized derivative of the spinor is equal to 0 on scry. All right, so that's the conformal formulation, and now we have some questions to answer. So the point here is that we have to say whether solutions of the unphysical Weil equation, so that's this equation here, exist, which satisfy the physical Witten equation on some space-like asymptotically Euclidean hypersurface, and which satisfy the Bramson condition on scry. So can we find solutions of these equations which satisfy the physical Witten equation on an initial data surface and also satisfy this equation on scry? All right, so that's the question. So in order to answer this, we have to have a look at the structure in this red region that I had on this drawing. So that's the structure where the asymptotic regimes are coming together. So this is based on work by Helmut Friedrich from 1998, where he came up with a new way of representing space-like infinity, which gives you access also to null infinity. And I'll describe briefly here how you get to this representation, even though this is very, very brief and it will not give you all the details, but it is really quite a tour de force to get to these things. But just to give you the idea. So we take an asymptotically flat vacuum spacetime, physical one, and we fix an asymptotically Euclidean hypersurface, sigma twiddle, and h twiddle is the induced metric. Then we conformally compactify this. So this is that's a Riemannian surface, Riemannian manifold, and we can one-point compactify them at an asymptotic end by adding a point to this, and we get a conformally related space-time and a conformally related metric H. The conformal factor between those metrics H twiddle and H is denoted by omega, and it satisfies these conditions here. That's the standard conditions for conformally compactifying infinity in the three-dimensional Riemannian context. So the conformal factor vanishes at this point at infinity, the gradient vanishes, and the second derivatives are proportional to the metric. In my conventions, this is -2 times the metric. Now, the conformal factor cannot be smooth, which means regular in all its derivatives, or all the derivatives cannot exist if the ADM mass does not vanish. And so there are singularities in the omega which are proportional in some sense to the ADM mass. So then you locate yourself at the point at infinity, and you shoot out geodesics from that point and introduce normal coordinates based on those geodesics, and you get a radial coordinate r and some angular coordinates which give you the directions in which you shoot your geodesics. And then those directions you regard as a sphere, and this is meant by this phrase here, that you blow up the point at infinity to a sphere, which is called I0. Okay, so then you have, at the point, you have a sphere of directions, which are the directions in which you have shot your geodesics, and r equals 0 is that sphere. That's a different way of doing this, yes. It is somewhat related, but it's this is three-dimensional still. The hyperboloid that you're talking about this one?
Yeah.
Yeah, that's the four-dimensional picture.
Oh, you're doing it in 3D.
This is, so far this is 3. Now I go into 4. Okay? So you have your initial hypersurface. And then we take a different class of geodesics, namely the conformal geodesics that was talked about last week. And we set up what's called the conformal Gauss gauge. So we have this class of conformal geodesics. We take the time-like ones, and we take the ones that start vertically from, so you have your initial surface. Here is the point at infinity. And then we start vertically into the future with these time-like conformal geodesics, and as long as those exist, or as long as they move, we can introduce what's called the conformal Gauss gauge, which is a way of defining quantities, or concretely you define a coordinate system, you can define a frame, you can define a conformal factor, and you can also define a what's called a Weil connection, but we won't be using that. So the important thing for us here is that we can set up a coordinate system based on the conformal geodesics. And we can find, or we can define a conformal factor for the physical, for the unphysical representation of the physical metric of the spacetime. So in order to get that physical, unphysical conformal factor, we choose initial values for the conformal factor, which is the conformal factor that we use to compactify the space, the hypersurface, and some divided by some positive function kappa, which will become r in just a few lines. So, but in general, this is some function kappa. So that's initial values, and then the theory behind the conformal geodesics tells you that you can actually solve an equation for this theta thing, for the conformal factor, where when you know the initial values, you know what the conformal factor is everywhere. And that's this formula here. So this is the conformal factor in the space-time. It's given by this omega over kappa, which is the initial value. And then you have this factor 1 minus kappa squared over r squared times t squared, where t is the parameter along the conformal geodesics. So this means that you have an explicit formula for the conformal factor given in terms of the location of where the conformal geodesic starts and how long you follow the conformal geodesic. So in terms of a coordinate system that is defined, adapted to these conformal geodesics. And this here tells you that when this parenthesis here vanishes, that theta vanishes, and that means that you are on scri plus or scri minus. This has two zeros. One is scri minus and one is scri plus. And so in order to make life easy, we choose this kappa here equal to r, so that this entire thing here vanishes, becomes 1. If you leave this arbitrary, then this kappa here determines where scri is located in terms of the coordinate system defined in terms of the conformal geodesics.
I mean, omega was going like something to make. Sorry, what was omega going like to make I0 a finite point?
Omega vanishes at I.
Sorry, omega vanishes at I.
Yes, and kappa beta also vanishes. I mean, that's an obvious consequence of this formula here. And so we make this equal to r, because r equals 0 is I.
Right.
Okay.
Oh, sorry, the r is the distance from. Sorry.
Yes. Yeah. Okay. So now we have the main coordinates here are r and t. So t is the time coordinate which goes along the conformal geodesics. And r is the distance from the infinite point. So r grows into the finite regions. So then with kappa equals r, we have these sets here. So scri plus minus is t is equal to plus or minus 1. I, that's a capital I here. This is given by r is equal to 0. So that's the sphere that I called I0, the sphere of directions. And then t runs from -1 to 1 because at t squared equals 1, this factor here vanishes. Okay, so when r is equal to 0, t runs between -1 and 1, and this is a cylinder, structurally a cylinder, and this is called the cylinder at spatial infinity. And then we have the special sets where the t is equal to plus or minus 1, and r is equal to 0. That's called the critical sets. Now this is very difficult to visualize, so that's why I help you here. So this is how I imagine this situation to be. So you have this cylinder here. This orangey thing here, that is the space-like hypersurface, or is a space-like hypersurface that goes to infinity, and at infinity it reaches this cylinder, and this line here, this here is I0. That's the line of or the sphere of directions. So here we have this color here. This is really scri plus. This down here is scri minus. Here in the middle we have the cylinder between t equals -1 and +1. And these red lines here, these red circles, which are really spheres, these are what's called the critical sets. Okay, so this is the situation of an asymptotically flat spacetime in this representation based on the conformal geodesics. And you see that this representation gives you access simultaneously to the space-like situations and null situation. But the problem here is with these red lines here, where things are, where these two regimes are coming together, and this is where all the problems are sitting when you're discussing spacetimes in this setting here.
So, I mean, by my understanding, there should be canonically a metric on the cylinder and then a conformal structure on the critical sets. Is that right?
I don't know.
No, the cylinder, I think, because we're asymptotically
there is a metric. In what sense this is conformal? Well, I mean, it's a conformal metric, yes. But it's not, I think, conformal in the sense that you mean.
No, yeah, I think there should be actually a metric on the cylinder.
Yes.
And
I do not know, but that's something we can discuss, certainly.
I mean it is natural to put the system metric on it. This is Schmidt idea, but I don't know how that ties into the Friedrich framework. They just separation of variables and then they sort of.
Yes.
But I don't know. I never heard anybody tell me that one could be lined up with the other.
I don't think it can be so easily lined up. There is a connection, I'm pretty sure about it, but you know,
well, I think you're saying that there's a canonical way to do that.
Yeah, I mean,
if it's canonical, then we should find it, right?
Sort of, yeah.
And you're talking world project.
Yeah, this must be somehow.
Yeah, I mean, we can certainly look at that. All right, so keep this picture here in mind. This is where things are happening. So what we are going to do now is look at the Weil equation in the, so the physical space-time is everything outside in these directions here, right? And so we are looking at the physical Weil equation in this area here, in this region, do a conformal rescaling in order to get towards the infinite regions here, and then see what happens to the to the solutions of the equations as we approach these red circles here, as we go to the critical sets. All right, so, and we do this now for Minkowski space. That's the easy thing, even though it's also messy. So when you look at the conformal or the cylinder representation of Minkowski space, and you introduce the adapted coordinates based on the conformal geodesics and the conformal factor, you find that the metric, the conformal metric, has this form here. The sigma squared is just you know, your favorite representation of the unit sphere, d theta squared plus sine squared theta d phi squared. The conformal factor theta looks like this, and you see that theta vanishes when r is equal to 0 or t is equal to 1 or t is equal to -1. So it vanishes on scri plus, scri minus, and the cylinder. So we have this metric, that's Minkowski space, in this sort of weird representation. We choose a spin frame adapted to, you know, to the structure here. We take null vectors L and N, just the usual GHP or NP formalism. M is a space-like unit vector on a complex space-like unit vector on S2. Again, whatever representation you prefer. L and N have this form, and then we can write down the unphysical Weil equation, which is the one that has this gamma term on the right-hand side, and that is this thing here. These operators here, eth and eth prime, are the unit sphere operators, are the eth operators on the unit sphere. All right, so that's the system of equations that give you the unphysical Weil equation. So here it is again. Now, when we are on the cylinder is r equals 0. And you see that r equals 0 means that those terms here drop out. What that tells us is that the cylinder I, this I thing, is what's called a total characteristic. That means that everything that happens on the cylinder stays on the cylinder. Okay, so you have some values. The spin field has some values somewhere on the cylinder. This will propagate along the cylinder, but it will not get out. It will not get out into the physical spacetime. So we look at this set of equations. This now is again a hyperbolic system on that cylinder in 3 dimensions. It's a system of PDEs because it has 3 derivatives here. And now, because we are in spherical symmetry, we expand these alphas, these components here, into modes. So we write them as multiples of the appropriate spin-weighted spherical harmonics. That gives us alpha k. So alpha 0 can be written as alpha 0 jm, where j and m are just telling you which spherical harmonic you're looking at. And then I'll just drop the j and m. So when I have this here, this alpha 0 here now means that we have a mode corresponding to j. This L here is j plus 1/2. So that's an integer here. And that characterizes which mode we are looking at. So we get this system of ODEs now, which have a parameter, a number that characterizes which mode we are looking at. So now we are sitting on the cylinder. We are looking at the values on the cylinder. And if I want to get any information about the behavior of the field outside, I have to look at what happens to the R derivatives. And in order to get those, I go back to the original equation here. And from this equation, I can derive equations for the what's called the n jets. So that's the nth R derivative of alpha 0 and alpha 1. All right. So I take enough derivatives of these equations, and then I can get an equation for the radial derivatives. And then I restrict back on the cylinder, and that gives me a system of equations that now has two numbers, namely the derivative that I'm looking at, that's the n here, and the mode that I'm interested in, that's the L. And L minus 1/2 is actually the spin value of the spherical harmonic. So we get these two equations here. Some observations. When you look at those, you see that when t goes to minus t, the two components interchange. And when you look at the coefficients here, 1 minus t and 1 plus t, you see that those are singular. They become 0 at the critical sets. That's why these sets are called critical sets, because the differential equations have the funny behavior. So it's a Fuchsian system on minus 1, 1. And the solutions may be singular at t equals plus minus 1. Now this is a problem, because when you have singularities at the critical set, that means that the equation, the Weil equation, will propagate those singularities to Scri, and then you have a singular field on Scri. And that's not what you want. So if we...
That's one of the things that people talk about a lot of long-term. So
yes, exactly.
Would you get a similar story if you had a polyhomogeneous expansion? In R?
No, what happens is that when you allow those things to become singular in t at t equals plus minus 1, you pick up log terms, and those then will be translated into log terms in R by the propagation.
So I'm not sure which way round we're going. So if you were starting with
I'm not looking. Yes.
Log terms, then that implies log terms at square, or is it which way round do we go? Or you have log terms at square?
I assume that I'm looking at initial values at t equals 0, and given depending on the initial values, this system here will develop log terms at t equals plus minus 1.
Oh,
so if I want to...
Even if there's nothing going on in R...
Yes, exactly.
They could be at
yes,
Scri.
yeah.
Because I'm sort of forgetting slightly the Kerr-Berger story, or...
Which story?
No, the Kerr-Berger, or maybe even...
Yes. Yeah, but that is, again, I don't think this is really related to this one. I mean,
actually, they would still have an ordinary... They wouldn't have log terms in R.
No, I don't think so. Okay, so if we look at solutions of this system here, we get solutions for arbitrary n, and that means that we can write down a formal power series expansion of the Weil field near the cylinder. without any statement about convergence or anything.
You can't just write down solutions to those equations?
No, you can.
Without parsing it? They're not some sort of hypergeometric equation?
No. Next slide. Yes, that's what they are. I mean, you can write down the solutions in terms of Jacobi polynomials, for example, or Jacobi functions, I should say. But I think it's better to regard them as generic hypergeometric functions because there is much more known about those. In any case, I'll do a transformation here from alpha 0, from the alphas to betas, which just take out some of the powers to make the equation simpler. And then we can derive second order equations for the which are uncoupled. So I have an equation for beta 0 and an equation for beta 1 only, which looks like this. And as you say, so these are Jacobi equations, each of those, and the regular solutions are the Jacobi polynomials. But more generally, I think it's useful to look at them as a hypergeometric equation because there's a lot of stuff known about those. And of course, depending on the values of n and l, you get a different character of the solutions. So different modes behave differently at different derivatives. And if you want to have a regular field, at least at t equals plus minus 1, you need to have special initial conditions. Right? So because the initial condition tells you what kind of solution you pick, and that will tell you what happens at t equals plus minus 1. So we need to find the relationship between initial conditions and at t equals 0 and the singular behavior. So initial conditions, we want to make a relationship to the Witten equation. So now let's look at the Witten equation on t equals 0. So that's the Witten equation in the physical spacetime with the rescaling that we have to do, where the conformal spinor is the same as the unphysical one. We get this equation, and that reduces to these two simple equations, which have solutions which look like this. And now you stare at this, and you see that you have powers of a square root of r, essentially. And you ask yourself, in what sense is that a smooth solution? So that took me some time to understand what really is happening here. But the idea is that in this representation, where we have the this on the space-like hypersurface, we have a one-point compactification, and we are looking at r equals 0. We are sitting at the infinite point, and then we are looking at spinors, and that means that at a point at r equals 0, the spinor components are double valued. So when I go around the point 360 degrees, the spinor components must come back to its negative or to their negative, and that's reflected in the appearance here of this of the r to the 1/2, and and that tells me that we should not expand in r, but we should expand in powers of square root r, and then we get smooth solutions. When you look at this in the framework of the spin bundle that is defined on sigma, you actually see that that's the right thing to do. Okay, so now we go back. We replace r by square root r, and then we look at the equations, and we get one of those second order equations now looks like this. The only thing that happens here is that the n is replaced by 2n or something, and the whole thing here gives you this equation here. And now we can look at this equation from the point of view of a hypergeometric equation by transforming this in the standard representation for the hypergeometric equation, and we find that it has, at these singular points, x equals 0, 1, and infinity, which correspond to t equals -1, t equals 1, and t equals infinity, we have singular points. And the equation here has a power series expansion near x equals 0, for example, which is defined in this way, which is the definition of the hypergeometric function for given a, b, and c, and so on. In our case, we have a and b are equal to plus or minus the mode parameter, and c is related to the derivative. And we can write down similar expansion at the other singular points. Now,
sorry, so x is related to t.
X is here. T is 1 minus 2x.
Oh, t is 1 minus 2x.
All right. So now we are in the realm of the theory of the hypergeometric function, and there is a great book that I discovered, which is by Felix Klein, Lectures on the Hypergeometric Function, and that gives you everything you wanted to know and more about the hypergeometric function. So we look at this and we try to understand the various cases that arise, and I have summarized this here in a preliminary statement because some of these things still have to be checked. So if we look at n even, so that is n is now gives us the derivative, the nth derivative with respect to square root r. So then we have those cases where the modes, these are functions of r then essentially. When we have functions of r, then all the modes with L greater than or equal to 1 are singular at -1, 1, which means that they develop into singular components or singular modes on scry. So we are forced to look at the odd ones, and for the odd ones there is some sort of a strange thing going on for low ends, which has to do with the asymptotic rescaling and things. I'm not going to go into the details here, but if we have n not equal to 3, then there is exactly one mode which is regular on -1, 1. All the other ones that one could look at develop log terms. Like those ones up here also, they also get log terms. So, but for every n, for every derivative, there is exactly one mode, or the other way around, for every mode, there is exactly one derivative that has to go together. And when you look at those regular modes, you find that these are in one-to-one correspondence with the modes of the Witten equation that I had written down there. So you can make a one-to-one correspondence of which derivative of a solution of the Witten equation at the hypersurface corresponds to which regular mode in the solution of the Weyl equation.
The log terms are coming from solving the differential equation.
Yes. Yes.
So
When you just look at one of those equations, choose an L and an N, plug it into Mathematica, and it gives you either an atan, a hyperbolic arctan, or a log something.
Boundary conditions that kills those log branches.
I mean, that's basically what we are doing. We're not looking at boundary condition, but initial conditions. Okay, so that means that if we are given a formal solution of the Witten equation on sigma, then there exists a unique formal solution of the Weyl equation, which is regular on scry. And it turns out that this solution is automatically asymptotically constant, so it satisfies the equation that Brian Bramson has written down. So that means that, at least in the context of Minkowski, things fit together in such a way that the statement that you want is actually true. So given a solution of the Witten equation, there is a solution of the Weyl equation which is asymptotically constant. And now the next task is to look at this in Schwarzschild And this is work in progress that we have not yet finished because it's a huge mess. Just look at the metric that you get for Schwarzschild in something that you know, exposes the cylinder, but not in a nice way as before in the Minkowski case. So we have the conformal metric is given in this way. The physical metric is then theta to the minus 2 times the conformal metric. Conformal metric is given in this way. Conformal factor looks like this. And this function g here is defined in terms of a function f, and the function f is this. So that's all quite nasty, and you need to use computer algebra for that. But in the end, we do get that we have the cylinder, at least part of the cylinder, exposed, so that we can look at or do calculations on the cylinder. The coordinate system here, as you can see, there is no dt squared term. So the dt is a null coordinate, or t is a null coordinate. And we have to be a little bit more careful here. It means that scri minus and the critical set I minus are not in the patch, and we do not have the obvious time reversal symmetry as we had in Minkowski space. And I'm not going to write down this in detail.
Sorry, just say, but you should. I mean, this time reversal is sorry.
Sorry?
Well, I mean, short sharp this time reversal is buried in.
It should be, and it will be.
Oh, sorry. Okay, but not yet.
No, at least not, I mean, in general, yes, you can find a different way of representing it, and then it's manifestly time reversal symmetric. But in this representation, it's not yet. But when I now look at these equations here, so I'm going through the same process as before. Writing down the equations, restricting to the cylinder by putting r equals 0, expanding into modes and looking at all the derivatives of the modes. And then I get a system that looks like this, where I have these functions here, a0, or all these a, b, c, and d depend on t. And so I have a left-hand side which contains all the nth derivative of the functions. And on the right-hand side, I have all the derivatives up to and including n minus 1. So this means that I can interpret this equation here as a linear equation for the nth derivative, where the lower order terms are sources, right? And so that's what I just said. The lower order derivatives are sources. When I look at the homogeneous equation, so I put m is equal to 0 here, then this part actually reduces down to the Minkowski case after doing some transformations. And those transformations that I need to do also restore the time reversal symmetry. And so from what this looks like, and this is something that we still need to work out in detail, it looks like that we can set up a recursive argument to get regularity of the nth derivative once we know regularity of the lower order derivatives. And that's the work that we still have to do in detail. The problem here is that even though these things are regular, they could be, because you have to integrate them, they could still give you singularities. But I hope this does not happen, but that's what we need to figure out. And then because this is dominated by the Minkowski case, so when m here is equal to 0, we are back in Minkowski. I hope that this will give us a very similar result as we have in Minkowski. So that's where we are at. The conclusion here is that in Minkowski space, we do get what we want, namely that we find solutions of the Weil equation which have the required properties. In Schwarzschild, we get a recursive system which seems to produce the same sort of result, but that's something that we still do not know quite yet. Now, if it is true that this holds in Schwarzschild, then we can go back to look at the Corvino construction, the gluing construction. Corvino and Schoen have shown that you can take an arbitrary asymptotically flat spacetime, you can cut away infinity and replace that piece by an exact Schwarzschild or Kerr spacetime. And so we can, and that gives us access to a large class of asymptotically flat spacetimes, because you can make this Schwarzschild piece very far out, and so it's only at the final asymptotic end that you have to do this. So that means that this result would hold in a large class of asymptotically flat spacetimes. And we still have not looked at the properties of the energy momentum density that is defined in terms of that field. That should be, once we have the a formal solution, we should be able to just plug that formal solution into the formula for P and then determine whether it's time-like and future pointing and so on. But that's something, again, that we do not know. And then, of course, if you are a pure mathematician, then you say, okay, this is formal power series. That doesn't tell me anything, but then I ask you to provide the rigorous proof of existence using the PDE theory yourself. So, and with this, I'll stop. Thanks.
A few questions?
Yeah.
Yeah, just a question about this the Schwarzschild case you're presenting at the end. So in that case, if I understand correctly, the metric isn't smooth at r equals 0 to have ADN mass.
Yes. Yep.
Yeah, I think.
So the conformal factor, this omega, is not smooth. Yes.
Right. Yeah, the spinor field that you were Witten, which is the Witten equation you're finding, you're either assuming or finding that it was smooth, as in all the derivatives that are.
It's smooth in the sense on the cylinder. On that cylinder, it does not develop singularities at t equals plus or minus 1.
That's right, but what about in R? Because you're computing the R, the nth derivative with respect to R or S.
Yes.
And evaluating that at R equals 0.
Yes.
So that's implicitly assuming those
Yes.
differences exist.
Yes.
So
Yeah.
how is that compatible with the lack of differentiability of the metric at I naught?
Yes, I know what you're asking, but I don't know how to answer.
Because they're kind of tied up in the Witten equation. Right?
Yes, but it's always only asymptotic, and so that's that. I don't know. I have to think about that. I don't know.
So yeah, I mean, the usual Witten argument says you just have an asymptotically constant spinor, and as a naive optimist, I would imagine that your asymptotically constant spinor on every space-like hypersurface going out to the cylinder would give rise to your preferred one, which then continues all the way up the cylinder and then turns into the asymptotically, the standard asymptotically constant spinor that you use to describe.
Yep.
Is there any obstructions to that picture? Or any
I don't think so. But
so why? I mean, as I said, it sounds naive. But tell me what's wrong with it.
I don't know. I do not see an obstruction to that. But again, I have not checked that. I really don't know. Yeah. I mean,
Now let's wait for the break.